So continuing with our discussion on Dunkerley's method, today we'll apply the Dunkerley method to a rotor system where the weight of the shaft is considered. In the previous video, we have solved the one numerical in which we have not considered the weight of the shaft. But in this particular problem, we'll consider the weight of the shaft, and deflection due to the self weight of the shaft is also to be considered. So we'll see the numerical. So a shaft with diameter 40 mm, Young's modulus as 100 GPa, and the density. Now here the value of density of the shaft is given. That itself indicates that we need to consider the self weight of the shaft. Had it been the case where the density of the shaft is not mentioned, that means you need to neglect the weight of the shaft. And since here the density of the shaft is mentioned, it indicates that you need to consider the density, the self weight of the shaft also. If you do not consider the weight of the shaft, then your numerical will not be correct and you lose marks. So whenever there is a density of the shaft is mentioned, you need to consider the self weight of the shaft as well. If it is not mentioned, then it indicates that you need to neglect the weight of the shaft. Okay. So here the density of the shaft is mentioned as 7850 kg per meter cube, and it is simply supported as shown in figure. So here in the figure, the shaft is simply supported, and on this shaft there are two rotors. One is of 100 kg, another is of 80 kg. 100 kg rotor is mounted on the shaft at point B, and 80 kg rotor is mounted on the shaft at point C. So two rotors weighing 100 kg and 80 kg mounted on the shaft. Find the lowest natural frequency and critical speed of the shaft by Dunkerley's method. Okay. So we know that Dunkerley method says that you need to consider one rotor at a time and consider it as a point load on a simply supported shaft. So first we'll consider the 100 kg rotor which is placed at point B. So this is how we modeled the 100 kg rotor. This distance is 800 mm, this distance is 200 mm, and by using this formula for the deflection of a simply supported beam with point load acting at some point, we have put all these values. The weight of the shaft is 100 kg, so 100 into 9.81. The distance B, this is B distance, is 800 mm. This is X distance, it is 200 mm. And then the length of the shaft is 1000 mm. The Young's modulus or modulus of rigidity is modulus of elasticity is 100 into 10 to the power 3, and this is moment of inertia of the shaft. So here we obtained the deflection due to 100 kg rotor only comes out to be 0.67 mm, and from this we can find out the natural frequency because of the 100 kg rotor only, and it comes out to be 19.31 Hertz. Then we consider the rotor at point C only, that is it is of 80 kg, and by using the same formula and putting the values, we determined the deflection as 1.19 mm, and from this deflection you can find out the natural frequency because of the 80 kg rotor only, and it comes out to be 14.39 Hertz. Now here in the previous problem there was no weight of the shaft to be considered, but in this problem, since the density of the shaft is given, we need to consider the self weight of the shaft also, and because of the self weight of the shaft there is some deflection in the shaft, and this shaft is modeled as this. Okay, so here the shaft is modeled. Since the weight of the shaft is uniformly distributed over the span of the shaft, So here this is the UDL, so uniformly distributed load with point load acting at the center. It is L by 2, L by 2. So this the entire weight of the shaft is concentrated at the center, equidistance from the two ends. This shaft is simply supported. In the Dunkerley method, you need to consider the shaft as simply supported only. So this is a simply supported UDL beam with point load acting at the center, and here the weight of the shaft can be find out. Weight of the shaft can be find out by using this formula, that is density multiplied by volume into acceleration due to gravity. And if you put the values of density, volume, and the acceleration due to gravity value, the weight of the shaft comes out to be 96.77 Newton. So this is the weight of the shaft. And the deflection formula for UDL on a simply supported beam with weight acting at the center, it is 5 WL to the power 4 380 upon 384 EI. When you put all these values, so here I have put all these values in Newton meter. Okay, all these values in either meter or Newton meter. So all these values I have put, and the answer comes out to be 1.0 into 10 to the power minus 4 meter. So here the deflection due to shaft is 1 into 10 to the power minus 4 meter, and in mm it comes out to be 0.01 mm. And from this I find out the natural frequency due to the self weight of the shaft only, and it comes out to be 49.84 Hertz. And by using the Dunkerley formula, 1 upon Fn square is equal to 1 upon Fn b square plus 1 upon Fn c square plus 1 upon Fn s square. So this S stands for the natural frequency due to shaft. This is Fnc, that is natural frequency due to rotor at point C, and Fnb indicates the natural frequency of the shaft at rotor B. From this I find out the natural frequency of the entire system, and it comes out to be 11.24 Hertz. And you can find out the natural frequency in radians, and once you find out the frequency in radians, you can find out the critical speed of the shaft by using omega n equal to 2 pi n upon 60, and the critical speed of the shaft comes out to be 674 rpm. So 674 is the critical speed of the shaft, where you will get, if the shaft rotates with critical speed, you will get the maximum deflection of this shaft. So this is another numerical where the self weight of the shaft is to be considered. So I hope you have understood how the self weight of the shaft also incorporated, and find out the natural frequency by using Dunkerley method. So thank you very much.